Okay, it's 8 o'clock. We will get started soon, okay? So today, as I said, that we would like to test on the memorization of the algorithms. And then next, we will go on to the recursion. So before we get started, first, what I want to say is a few things. The rules. Okay, each problem will give you 7 minutes. Okay, each problem will give you 7 minutes. And you will get started, and I have the timer online, so you will see the timer on the clock, okay? So you see that. So rule number 1, don't use any IDE, just use text editor. Okay, the reason why we do this because that we don't want you to have the grammar checker, because you need to memorize the language, and then you don't have a grammar. And in fact, we don't look at the grammar that much. We don't check your syntax error too much. Overall, we look at the idea, whether you got it or not. Okay, that's number 1. Number 2, if it is a binary search, assume data sorting. You don't need to do sorting. Okay, you don't need to do sorting before binary search. Then third one is that each problem will give you 7 minutes, okay? Each problem will give you 7 minutes. And you use the editor you have. And then after that, you are supposed to give us a .txt file. I don't take Java file, just give us TXT file, because Java file maybe from IDE. So we don't take .java, which only take .txt. If you do not submit .txt, you just fail. Okay, you just fail. Okay, these are the rules. Any questions so far?
No.
I have a question.
Yes.
Is it just we only have to like write the method, right?
Just the method, yes. No
Okay.
testers. No tester needed. Any other question?
No.
Okay, we'll get started. First, if we don't talk about it, then assuming that you have an array of integer a equals 5, 2, 4, 3, 8, 9, 6, 7 data is used, okay? And then again, binary search, we array sorting. Okay, you actually do the array sort before you do binary search. So you don't need to write the array.sort. We are assuming that the data already been sorted. So these are the data we will use. Okay, so this one I also post to the group. So when you don't have the data, but in fact, you do not need the data. Okay, you do not need the data. It's just for your reference. Okay, now, so the rules and the data we post in the group, in the Facebook group. Now the first problem. Okay, write a bubble sort. Okay, the first problem, this is problem 1, write a bubble sort. So get your editor ready, okay? Get your editor ready. We'll get started soon. I'm sorry. The problem number 1.
Well, Dr. Chow,
Hmm?
well, after we're done, do we send it to you on Facebook?
On Facebook, the text file, you can send it to the Facebook group or send to my Facebook account or send to the chat box.
Okay.
Don't send to email because email I need to check somewhere else. So get your editor and be ready. We'll start the 2 timing, okay? This first one, I'm more relaxed. Okay, we'll get started. Everybody ready? Everybody ready?
Yeah.
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 How about Kirsten?
Yeah, I'm ready.
Okay, how about John? Hello?
Yeah.
Okay, go ahead. Okay, hands up. Please submit your answer, okay? Whatever you have so far, okay? Whatever you have so far. Okay, please submit. We will have 1 minute break and then we will start a minute later for the second question, okay? Please submit right now. For the answer, I'll check later, okay? For the answer, I'll check later. After class, I'll check after class and give you each one 25 points and we'll test four questions. Okay, second problem that we will work on. Second problem we'll work on the we will work on the recursive version of the binary search. And you need to write the main function and one helper function. Okay, helper functions then a helper function needed. So two function in total. So the non-recursive version, I think you are okay. So here we test you on the recursive version, okay?
Wait, Dr. Chow, you
Hmm?
said also at the main, right?
Both two function needed.
Yeah.
It's not the main function, it's the main binary search function. Don't try to confuse everybody else. Okay, that's the question we have. Okay, now everybody ready? Hello?
Yeah.
Yes.
Yeah.
Okay. We'll get started, okay? Go. Okay, time's up. Submit, okay? We'll get ready for the next problem. Submit, okay? Give you 1 minute to submit. Okay, everyone submitted. Now, next one, we are going to work on the problem 3. Problem 3 will be on merge sort. Okay, so you need to write a merge sort of the array. Okay, under the assumption that merge is available. So you don't need to write the merge function, assuming that you already have the merge function, because we don't have that much time to write the merge function. So you would have the merge function. Let's assume that this one already been designed by somebody else. You don't need to do that. So you just write the merge sort. So you actually enter integer array A and B when you call it, and then you return C. Okay, that's assume that that function already available. And then you need to design this merge. So it's recursive. You need to return the final sorted array. Okay. Okay, so this is question 3. Okay, let's get started. Okay, everybody ready?
Yeah.
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 Okay, let's go. Just the merge sort itself, okay? The merge function assume is ready. You can just call it. Okay, time's up. Please submit, okay? We will have 1 minute break and we'll start at proper 4. Okay, problem 4 is on selection sort. Okay, this one no extra condition or extra function. Okay, everybody ready? Hello?
Yeah.
Harrison, are you ready?
Yeah.
Oh wait, does it all have to be like recursive?
Hmm?
Does it all have to be recursive?
No. Just
Okay.
the sorting. Only the binary search need to be recursive. Okay, now we have the selection, so everybody ready. We'll get started, okay? Go. Okay, submit. So we will have a break because you are very tired right now, okay? So after you submit your data, you can have a break, come back on 8:50, okay? Come back on 8:50 p.m. After you submit, you can have a break, okay? And I will grade it after class. Each problem will be 25 points. I'll give you a total points, okay? Have a break. Okay, I'm sorry. We actually passed the 8:50. Any questions so far?
No.
Okay, so today we have this in-class test, okay? And then we are going to the last chapter, recursion. Let's actually review a little bit. Basically, this course, APCSA, we have first we teach you the language and the syntax, Java language and syntax. At the same time, I want you to go through the solo learn Java first to at least know some syntax. Then we go into the program structure. And then this program structure, we use a coding back to do it. And we start to have a basic algorithm. So there are maybe more than 100 different algorithms, simple algorithms in the coding back. And then we also teach you this recursion, sorting, these different algorithms. So you have to review it and then make sure you memorize each individual one. And then past this level, this one, we are going to the problem solving level. We'll get started for user code to solve problems. At the same time, you will pick up object-oriented programming and also some other topics like dynamic programming, like greedy programming, like ad hoc solution. Okay, those kind of the ideas. So we actually structure this course one by one. Okay, so right now this syntax and program structure are almost done. And we are down to the last chapter for recursion. Then we will move on to the next course. Okay. Anyway, let's get started. So we talk about the iterative algorithm, for loop, while loop, more. And now this is the time we actually officially introduce the recursion. So basically, first you need to know about what is recursion and what is basic recursion. And then you need to know about what is tail recursion and what's good about tail recursion, why people like a tail recursion, and how you actually write a function with accumulator. And then you write a recursive function with running index. And then you work on using the recursion to solve problems. So these are different topics covering the recursion. Okay, so first you need to know about the real world problem. Real world problem, they do have a lot of recursion. So I think the lady maybe is standing right here. And there's a mirror, it mirror back, and then 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 mirror back. So you will actually see that there's the recursive mirroring in the mirror. And how many of them? I don't know. It actually keep mirroring until that the resolution is too low, you cannot see. Okay, this is one thing that you actually see the recursion in life. Second one is the fractal. Fractal is computer art, but usually it's generated by the recursive function. Okay, so this is another real world problem for recursion. And then when you do recursion, you need to read the recursive pattern first. So for example, 1/3 on here, 1/3 on here, 1/3 on here, and you mark this region as blue, and there's a line. Keep doing this, you get a recursive pattern like this. So 1/3 on here, 1/3 on here, 1/3 on here, and this one is recursive code of this one. Until it is too small to divide. Is that okay so far?
Yeah.
Yeah.
So to write a recursive program, first thing you need to do is to read, to figure out what is a recursive pattern. What is the same structure that you have right now, and you are trying to solve a smaller problem recursively. Okay, so you need to break down the recursive patterns. So another things that you want to look at this recursive rectangle, 1/3 on here, 1/3 on here, 1/3 on here, 1/3 on here. And then you cut a 1/3 here, 1/3 here, 1/3 here, 1/3 here. You keep putting this square at the 1/3 point, and then keep doing that. It looks like a rose, but it actually is a recursive rectangle. Okay, so this one is not. And then you actually do math to calculate the 1/3 point. Anyway, that is fractals. Okay, so fractal is a geometrical figure that just like triangle, circle, or rectangle, but fractals can be divided into parts, which is a reduced size copy of the whole. Okay, so one of the example is a Sierpinski triangle. So this is Sierpinski triangle is very famous. It's also a triangle. You cut half here, half here, half here, and then you connect it as a triangle. And then each small one on top, bottom right and bottom left, you continue to recursively calling it. So 1/3 on half, 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 you get another triangle. So this is level 1, this is level 2, this is level 3. You can keep doing that until level N. Okay, this is Sierpinski triangle. So right here, we do not go into the detail of Sierpinski triangle.java. You can download code from internet, okay? So now we go into the basic recursion. We want to look at the recursion first. Okay, we want to go into the recursion first. So before we go into the recursion, let's look at the normal for loop. So typically we write a program called Rocket. Rocket would do down counting until 0, and you will press off. Okay. Okay. First thing, we would like to actually write a function that's called Rocket. So this Rocket, you will do down counting. Okay, let's assume that you will down counting for n. So here, let's say, actually, let's run Rocket of 10. So you're down counting from 10. So what you would do using for loop would be for integer I equals 10, n, I greater equals 0, I decrease. Okay, here let's actually do I greater than 0. Okay, and you will do this. Every time you do system.out.print, you do down counting, so you do plus I plus exclamation mark. So you started from 10, 9, and then keep down counting to 1. And then here you would do this. When you get out of the loop, it is for sure that your I equals 0. Okay, you get out. When you get out, I equals 0. Then you will do this. You will do system.out.print line. Okay. Press off. Okay, so basically this is down counting. You count from 10, 9, whatever, down to 0, and you do press stop. Okay, that's wrong. But this one is usually using the for loop, regular for loop. Okay, it's using regular for loop. Now, if we want to write it recursively, okay, so this version I call it Rocket R. So this Rocket R, you also get an integer n. Okay. So first one, you need to determine the termination condition. When you get out of the loop, it's the termination condition. So your termination condition, you do this. So right here, n equals 0. You do the following thing. You do these two things. Okay, so this is termination condition. That means you will stop right here when n equals 0. Otherwise, you will actually do down counting. So you will print out there's a bug, okay? Here, this one I'm writing has a bug. I'm going to talk about where is the bug later. But you write out your this, and then you recursively call in this. So let's compare these two. This termination condition is in the here. This loop body is right here. This one you have a recursive. It's actually the loopback on the loop. Okay, so your loop can be right into a regular recursive call very efficiently. This one no return value, so just directly call. Okay, this one because there's no return value, so no return, just directly call. Okay, so here you actually do rocket 10, and then let's change line. And let's do rocket R10. Let's see if there is any difference. In fact, the second recursive call function right now, there is a bug. I'm going to talk about the bug later. Okay, but let's assume that here, let's try to run it. There's no problem right now, okay? You do compiler, there's no problem. But you run it, something bad happen. You keep deducting your number, you never end. Okay. Logically, the termination condition is here, recursive condition is here. So what did I miss? Harrison, where do I miss?
I'm not sure.
How about Jiang, where did I miss?
I think you should put a return after the system.out the print line.
This one. Here you need to put a return. Right? That's okay. Okay. Now, if I don't want to do this, is there any other solution that I can do? This one, Keyston. Do you have other way to modify the program to make it correct?
You can just put else around the rest of the stuff.
Yes, so two ways you can do it. One way is you put the return on the if statement. The other one is do else. So when you put this else, let's look at the if n equals 0. If n equals 0, you run this. And then when you are done, you get out of the else part and you go to here. You go to here, the program finished. Effectively, you got a return right here. Okay, effectively, you got a return right there. So you can actually use this if else to have the termination condition and the recursive condition. Okay, this portion that's called it recursive formula. Okay, you need to have a basic version and you need to have a recursive version. And then it is an else relationship. But you can also put a return and then you don't need that. Okay, you don't need the else part. So either way would work. Okay, either way would work. So this one is to show you how to convert a for loop into a recursive function. So ideally, one recursive call equivalent to one loop. Is that okay? Usually, one recursive call is effectively to one loop level. If you deny it correctly, you can convert from iterative call to recursive call, from recursive call to iterative call. Okay, that's the first thing that we talk about. Next one. This one we are going to talk about sequence. Some of you may not have the math yet, but trying to understand it, okay? So this one we talk about sequence. So a sequence can have A0, A0 equals 0. A1 equals 1. A2 equals 2. So continue, and then you will figure out this one. A n equals n. Okay. So this one we call it implicit formula. For the sequence. Now the question is, what is recursive formula? Okay, this one for Belinda. Have you learned the sequence or no?
Like arithmetic sequence?
Yeah.
A little bit.
So what is the recursive formula for this sequence we write on the left?
I'm not too sure.
You take the honor precautions right now, right?
Yeah.
You have to know it, okay? This one you have an it is equal to a n minus 1 plus 1. Given the fact that a0 equals 0. This one is the base condition. This one is called recursive formula. Okay, sequence you are supposed to learn it in Algebra 2 or in honor pre-calculus. Okay, either way. If your teacher doesn't cover it, then that's their problem. They did not cover the required material for you. Okay. So this is called recursive formula. So when we say recursive, that means your current term is determined by a previous term, or you call the term itself recursively. Then this one is a recursive formula. Okay, in this case, this one is defined by this one. Okay, the current term is defined by the previous term. It's called recursive formula. Okay. So given the fact that this kind of sequence, you can use an array to create a sequence, but you can also create a recursive function for the sequence. Okay, so this is your recursive function if you put the sequence into a function. Okay. So this one, you can generate a sequence by recursive function. So in a way, sequence and function, they are strongly related. Okay. Any questions so far?
No.
So here you do have a termination condition. That's your base case. And then every time you get your recursive deformation on your sequence. So this one is the sequence that we talk about. Okay. So now that they actually, when you write a recursive function, you need to know about the base condition. That's also called termination condition. In the for loop or while loop, termination condition is the exit condition. So while A, you do something, and then when you get out, it's not a condition, will be true. And we call it exit condition. Okay, you must have this. Then you need to have a recursive formula that do divide and conquer like a merge sort, or do incremental design. Okay, change or recursive formula. These are what you need to design for the recursion. So you do have this kind of the explicit formula versus the recursive formula that we talk about it in program. Okay, countdown recursion. And then this is the Rocky countdown. Anyway, that's fine. Okay. So then next one is your countdown recursion with return value. You may also have a counter, and then you actually have the return value. And the next one is recursive sum. Okay, recursive sum. So recursive sum happens when you have a summation of I from 1 to 10. So this one would be 55. It means 1 plus 2 plus 3 plus 4 plus blah, 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 plus 2, 10. Okay, this is recursive sum. So you can do a for loop. So you can do a for loop to calculate sum. Okay, but here we can write a recursive function to calculate the sum. For loop I don't cover. Okay, everybody know how to do the sum for a for loop using the for loop. Okay, so this is recursive version. So let's assume that you have sum of 0 is sum of 0 equals 0, equals 0. Sum of 1 equals 1 equals 1. Sum of 2 equals 1 plus 2 equals 3. Sum of 3 equals 1 plus 2 plus 3 equals 6. Okay, this is sum of something is equivalent to summation of I equals 0 equals 1 to n for I. Okay, so if you have a sum I, a sum n, is that okay? Hello, is that okay?
Yeah.
So this one is to, you got this, so this one we call it series. Okay, series is the sum of everything. So first we talk about sequence. Then we talk about series. Series is the sum of up to n. So right here you do this. Okay, so let's do it. Okay, sum 1 to 10. Here your application condition set n equals 0, return 0. That's the same. Okay, that doesn't matter. Because 0 sum is 0, so it doesn't matter. Okay, so this one is sum. Next one, we are going to talk about product. Factorial function. So factorial function is that you have 5 band, should be equal to 1 times 2 times 3 times 4 times 5. It also can be written down as pi. Pi is product. Pi and then I equals 1 for I to 5. This one we also call product of 5. It's called factorial function. Is that okay so far?
Yeah.
So we calculate a combination number and another number based on factorial. So this factorial number is very important. Okay, so luckily enough, we just copy this sum function, put it over here. Here we change it to factorial. So with n equals 1, you return 1. Okay. And then if here you actually change to factorial n minus 1, here we change it to time. The program structure is the same, only the operator is different. Okay, otherwise the program structure is the same. It's called factorial of 5. Okay, so this is recursive code. We have the recursive core and recursive sum. Now next one we will look at a problem. So right here, what you do like this one, let's look at the sum. So you call your sum of the 10 is equivalent to sum of the 9 plus 10 equals to sum of the 8 plus 9 and then plus 10. So you keep going until you have a sum of 1. This one is 1. And then you plus 2, you get sum of 2. Okay, so once you finish the program, your program code is like here you have sum of the 10. You keep going, you call sum of the 9. And then when you finish, you come back to sum of the 10. But here you need to plus not 10 again. So there are more operations you need to do. Okay. And this we consider too much of the context switch. Your operation system need to switch too much. So this type of function is not efficient. Okay, it's not efficient. So we need to change it to a function, we call it tail recursion. Okay, before we talk about recursion with accumulator, let's look at the tail recursion. So tail recursion is necessary because your recursive code usually is slower than your for loop. Okay, because you have too much of the context switch. Your function call, you need to push your function's parameter into the call frame and then pop out, push pop, push pop, push pop. Okay, that take too much time. So basically your function call is like call to subroutine and then call to subroutine, call to subroutine, call to subroutine. Come back, you still need to do something. Come back, you still need to do something. Come back, you still need to do something. Come back, you still do the new stuff, something. So here, have extra operation need to be done in the previous function call. So this one is non-recursive, tail recursive function. So tail recursive function is you call a subfunction, call a subfunction, call a subfunction, call a subfunction, call a subfunction. At the end, it returns right away to the top level. So the return part is much faster. Then it depends on the tail recursion. Okay. So which program has a tail recursion? Right now, this one is non-tail recursion version. Okay, non-tail recursion version. So you keep pushing your data into your stack and pop out whenever you finish. Okay, so tail recursive version, you will actually optimize it. So your call, after your return call, there is no more function call, no more operation. So right here, this one is not tail recursion because after you return from the previous function call, you still need to do some math. That's not tail recursion. Okay, let's write a tail recursive version of the sum number 2. Let me call it sum tail recursion. So the same sum program, we will write a tail recursive version. So right here, let me copy the main function over. Okay, so in order to write a tail recursive version, we have a public static, okay, integer sum. So you have integer n, and then you have an integer accumulator. Okay, so this one is a recursive call with accumulator. And you perform like this sum function as well. Okay. So now you got the accumulator. So if actually n Okay, you should have another index. You should have another I. Okay. So if I equals, I'm sorry. No, you don't need the I. Take out the I. So if n equals 0, then you will return your accumulator. Else you return sum of the n minus 1 and your accumulator plus n. Okay, so right here, you will pass the number into the next function call. So here function call pass to the next function, pass to the next function. Once it return, there's no operation need to be done anymore. There's no more that you need to done. There's no plus sign and no multiply need to be done. So this one is a tail recursive function with accumulator. But your original function need a sum of the number n. So this one actually is a helper function. You need to write the original function. So the original function is like this. You write down this. Okay. Any questions so far?
No.
So this one, we also want to copy it for the factorial. Let's copy. So right here, when you have the n equals 0, factorial is using multiplication. So you need to start with 1 instead of using 0. Okay. Okay. That's it. This one is a recursive function with the accumulator. Okay, get the same result. Any questions so far? And this version, the compiler can optimize the code so it will be faster. Okay. Any questions so far?
No.
Okay, so this one is a factorial. Fibonacci number, we talk about it when we do the algorithm study. So here we don't repeat. Okay, here we don't repeat. If you miss it, that's your own problem. You miss the class, we don't care. So helper function, we have the helper function now. Now let's look at another issue is the running index. Okay, now this one is also a sum function, but we are going to go over the sum of the array. Okay, let's use the 7 numbers formula. So let's assume that we have an array, we want to sum them up. Okay, so right now you have an array. and you need to add one by one. So if you write the for loop, it's very simple. Okay, so this one pretty simple, right? You write this one. Okay, so this one is a regular version. Now, if we want to write a recursive version, as I mentioned, your recursive code is just like a for loop. Okay, so your original function may be just a sum of integer array A, but you want to write a helper function first. So this helper function, you will have a running index. So let's call this running index as an integer I. Okay, and then you will write this, you will do if I equals a length, return 0. Otherwise, you return sum of the A and then I plus 1 plus A's I's value. So this one is a helper function without accumulator, and your original function should be public static integer sum of the integer array A. This one should return sum of the A and then index starting from 0. That's the starting 0. So here, your 0, your starting index is there the same as your initial condition. This one exit condition, and this is A, here should be A bar. Is that okay so far? And
Yeah.
I plus plus is right here. So this is the way you systematically converting your for loop into a recursive function. Okay, but this one is not a tail recursive version. So let's write another tail recursive function. I'm sorry, this is not helper function. Let me cut it, put it here. Helper function is this. This one is original. Now let's actually write another version that's actually original. Public static, okay, integer total. Okay, let me write the helper function first. Okay, so this one comes with accumulator. This version is different from the previous one. So if I equals a length, you run out of the numbers, you will return the accumulator. Otherwise, you will return total of A and then I plus 1 and then accumulator plus A's I's values. So you will call your total function with A and then 0, that's I equals 0. Then your starting accumulator is 0. Is that okay so far?
Yeah.
Okay, so sum of A and total of A. These are one with the accumulator, one without. They get to the same result. Okay. Any questions so far?
No.
No. No. Next one. Last time we talked about recursive version for recursive code, for the binary search. This time, let's try recursive function for selection sort. Okay, selection sort, but recursive version. So right here, let's actually get the same array that we want to have. Okay, now we want to write a selection set. Okay, I'll write a helper function first. So let's assume that you get an array integer A. You also want to have an integer I. And this I, let's assume that you're doing the so-called selection sort. So this is the to be swapped location. So to be swapped location, to be swapped location, to be swapped location, to be swapped location, until this one, right? The last one no need to be swapped because it's only one element, no more to be swapped. So you have the index I that's yours to be swapped location, and then that's fine. That's the outer loop. So if I equals A the length minus 1, you down to the last element. Your to be swapped location is the last element. Then you return, you do nothing. Right? So here next one you will do this. Next one you will do the following things. You actually pick the to be swapped location, and then you go through the whole array to find the minimum index, and then swap these two numbers. Okay. So basically, what you would do is actually you would do minimum index J would be equal to min index of your A array, and you starting from I, and then your current index. Let's see, your current index is 0, and your min index, minimum index is actually I. Minimum value is A's I's value. Let's see, let's try again. You actually get started from I, and then your minimum index is I, and then your minimum value is J. Okay, you do recursion to get it. Now let's write the minimum index function. This is the second helper function. So it's two-level loop, so you need to have the second level function. You return the index. So this is min index. So your integer A, and then your integer starting integer I. No, your current index is 1, only 1 is enough. Okay, let me see. Oh, no. you also need to have the minimum index and minimum. Okay, these are what you need to find the minimum index. So if I equals a dot length, you run out of the index, then you return minimum index. Here it should be star. Okay, if your star equals the data length, then you have this. Now, if A is a star less than minimum value, then you will return minimum index of the A and then star plus one. Continue to search the next one, and your current minimum index would be star. Current minimum value would be A star. Otherwise, your current value is not smaller, then you return minimum index of the A star plus one, and then the minimum index remain the same. The minimum value will remain the same. Any questions so far?
No.
So you got your I and you got your J. You got your I and your J, so here. Swap it. I is your to be swapped location. Okay, so this one is swap part. After you swap, you will recursive call the next one. So you return selection sort to the next to be swapped location, so I plus one. So here, your original selection sort is 2 for loop. Now you convert it to 2 recursive call. Outer loop, inner loop, inner loop. Inner loop, the recursive call is right here. So one function usually equivalent to one loop in for loop. One recursive function usually is equivalent to one over there. You see something wrong. So this selection sort, there's no return value, just recursive calling. This void type. Okay. Now, this one selection sort is helper function. You need to write the original function. But just have a parameter of the array. This one you'll return. Okay. It has no return value, so no return. I'm sorry, I keep making the same mistake. But you need to call the arrays library. Selection sort A. Is it wrong spelling? Selection sort. Okay, let's do it. Okay, sorted. Any questions so far?
No.
Okay, we are 9:50 already. Anyway, today we have a in-class testing on the recursive code. I'm sorry, on the recursive binary search, selection sort, bubble sort, and the merge sort. Okay, and the in-class testing is very popular in computer science class. If you go to college, it's actually like very often you will get those kind of tests. Okay. We actually try to prepare you to be ready for college. So that's something you need to do, okay? And then force you to memorize all of the algorithms just will help you to get familiar with all of the sorting algorithms. Later you will need them, okay? You not only needing them, but you also need to be able to convert a selection sort into recursive version. You can also try your best to convert the insertion sort into recursive version. Bubble sort can also be converted into recursive version. Up to you, okay? Up to you. You can practice that. Is that okay so far?
Yeah.
Even though it's not tested in AP exam, but you come here to learn computer science, you're not coming here to learn the exam itself, okay? So that's something you should practice. So today we are up to here, making sure that you have the overall idea of what recursion is. We kind of not having the full session today, but we tried the best to cover the necessary material. And then we will move on, because we need to save some time, we will need to move on to the next course. So next week, we will start the next course, APCSB course. Originally, it was a part of the AP exam. There's a separate exam called AP Computer Science AB. So we'll cover the same material like 15 years ago. I'm sorry, already 17 years ago. Okay, 70 years ago, this is the format that they use. Recently, still some teacher try to say that they should bring back this AP Computer Science AP course, okay? Because the current A course is made too simple, not able to support students to go to the CS major in college anymore. It's way too simple. So if you search this one called AP Computer Science B bring back, okay? So here you can see that a lot of people discussing college people need to bring back the AP ComSci AB course. Okay, so there was an AP course. There was an AP course. Okay. But somehow it's just like physics C, and later not a lot of people can do physics C. So some high school also cancel physics C, E, and M, something like that. Okay, but in a way, you are a student, you need that. Okay, in a way, you are a student, you need that. Otherwise, you cannot connect yourself to college. So that's what we want to do right now. And then also, it will prepare you for the user code bronze. Okay, so we mix the two things together. You cover the OOP and also competitive programming ideas. Okay, so these two are what we want to focus on. And some of the set map, you need to learn OOP before you know it. Okay, so in a way, this course is still very strongly in need if you want to become a CS major in college. Okay, your APCSA will just be a kind of the high school course from now on. It's too easy, no longer enough to cover one semester in college. Okay, it's only one semester in high school. Okay, anyway, that's it for today, and see you next week for AP Concept B. Okay, good night, everybody.
Thank you.
Thank you.